And next speaker, last but not least, Dr. Eugene Krissenel. Dr. Krissenel leads the core group CCP4 since 2009. Before that, he worked in PDBE, and there he became known to structure community for his work in field protein-protein interaction and protein structure analysis. His software for protein-protein interaction and oligomeric state analysis and prediction by PISA and protein structure alignment descent are widely used and regarded as de facto standard tools in the field. So over to you, Eugene.
Thank you very much, Maria, for excessively nice introduction. I just tried to figure out again how to share my screen. Really embarrassing a little. All right. Now I guess you should see my screen. Do you?
Yes.
Okay. Hello. Okay. Good. All right. So I start my presentation, and welcome to the very last presentation of this meeting. I realize we are running behind time, and I will try to keep it short. So it is a real pleasure to have this opportunity today to talk about CCP4 Cloud project and to discuss its current state and future perspectives. I'm not going to speak about solving structures with CCP4 Cloud. This was presented by Maria and myself at lunchtime bites, so please check recorded presentations if you are interested in that. It is very tempting to start this talk with the discussion of benefits in using cloud. However, after CCP4 Cloud project was first announced at Study Weekend some 5 years ago, the whole world changed so much toward the online way of life, and it's now easier to address just the concerns associated with working online. I personally can really think of only a few of them. Many of us have discomfort of using something which is not under our complete control. I don't know what to say here. These days, all our life is already given up to cloud through using smartphones and emails and so on. So this point probably fades away indeed. Next comes the fear of being disconnected when we need to work abruptly. But really, internet is now as common as electricity supply. And can you really imagine doing research without internet these days? I guess not much. Data security is a very much legitimate concern. But you may be surprised to learn that today the biggest security link is actually your own laptop, rather than internet lines or servers for they are managed professionally by dedicated teams. But the functional scope of cloud solutions is indeed a very good question to address. Until relatively recently, online crystallography was a bit fragmented and provided only bits of required functionality to users, such as, for example, model building or phasing. And for complete structure solution, one would have to use make extensive use of offline tools. What is the situation in CCP4 Cloud today? And let's have a look at that. CCP4 provides a complete structure solution package, which can be roughly presented in 10 functional categories as in this slide. CCP4 Cloud actually delivers on all of them in a set of about 68 coarse-grained tasks, which are built on top of more than 200 individual CCP4 components. And altogether, they give a structure solution line from A to Z with a generous choice of options in best CCP4 traditions. This makes the development of CCP4 Cloud largely completed by now. We still do introduce new tasks when necessary, but rather try expanding existing tasks for keeping the system concise and manageable. It is fair to say that CCP4 Cloud functional scope is equivalent to what is provided by desktop goods, really. From day one, CCP4 Cloud uses a conceptually synergetic approach to the design of all its components, which allows for a natural integration with third-party developments and web resources. Examples are many. They include access to global phasing software, ARP work from MBL Hamburg, integration with data retrieval and deposition services of the protein data bank, AlphaFold database from the EBI recently, importing data from other structure solution frameworks, and many others. There are 3 levels of automation in CCP4 Cloud. First level includes a full set of automated pipelines for image processing, structure solution, model building, refinement, validation, which are routinely distributed by CCP4. Second level provides navigation in structure solution process using some inbuilt logics, and also by learning template situations and their development through analyzing user actions. On third level, which was presented by Oleg Kovalevsky 2 days ago in this meeting, CCP4 Cloud automatically unfolds the whole structure solution project and leaves a user to deal only with fine details, in ideal situations, of course. We are planning on further enhancement of automation in CCP4 Cloud. A good interface should be self-explicable, and it should not require much documentation on its own. Yet CCP4 Cloud is more about science than program interfaces, and therefore approach to documentation is taken very seriously. Our documentation is focused on the essence of cloud tasks rather than interface features, and it includes a set of tutorials and demo projects for self-education and use in workshops, schools, and courses. Documentation repository is open for contributions, and everybody is invited to join the project. Here, the possibilities are really endless. For example, if you need CCP4 Cloud for your university courses, you can put up your tutorials on the cloud and use them right from there, which is really convenient and is already exploited by many people. CCP4 Cloud sees reasonable take-up figures. The cloud setup at Harwell, CCP4 headquarters, is open for global public use. Currently, it has over 2,000 user accounts, and it delivers over 70,000 jobs a year consistently. Besides the CCP4 Harwell site, there are a few more CCP4 Cloud instances which are maintained in various locations. They are set up to serve researchers from particular labs, institutions, and industry sites. But this nice picture would not be complete without questioning what happens with CCP4's graphical applications in the cloud. Can they be used? The answer is yes, but not without a limitation, unfortunately. They require CCP4 to be installed on user's machine. Certainly, this does spoil the whole picture. 2 days ago, Dale Turnroad gave us an idea of how structures were modeled in pre-CUDA era. That was possible, as we learned, but it is better than with CUDA. So having CUDA and molecular graphics is absolutely essential for the cloud success. I'm happy to reveal here that there are plans for new CCP4 graphics projects in CCP4. The project will be a rare opportunity to overhaul the existing graphics developments, specifically CUDA and CCP4MG, and make them suitable for using in cloud without having CCP4 installed locally. Job advertisements are indeed expected to be out in nearest months, and interested candidates are strongly encouraged to apply and look out for them. Image processing is another interesting and important area where dedicated graphical front ends such as GUI, Dell's GUI, IMOS field, not shown in this slide, sorry, and XDS GUI are used. These days, automatic processing at synchrotrons becomes progressively more common, and this is very good. Yet, the manual approach still needs to be exercised in difficult cases. Getting these applications fully into cloud may be indeed a simpler task on comparison with rewriting CUDA and CCP4MG. But here we face another challenging point. The point is that image data is big. Sometimes it is simply huge thanks to modern high-resolution detectors. Conventional way of dealing with raw data includes processing at synchrotron, as I mentioned, or downloading to local machines. If you wish to process image data in cloud, it needs to be uploaded there, obviously, and that is hardly feasible if you consider local sites due to the data size. The proper approach would be, of course, pushing data directly to the cloud. However simple this idea is, it has breathtaking implications, which I will speak about further. Structural biology is driven by data, and the data production line is very well established in our field. It has distinct stages of sample preparation, data collection, structure solution, storage, distribution, and utilization. Currently, structure solution is performed in local labs, and all information about it, intermediate data and metadata, remain largely in those labs. With data management practices varying from site to site, some studies suggest that shelf time of completed projects may be as short as few years. Depends on the site, depends on the culture, depends on the project, but it may be not too long. And here we come to the point which was raised by John Halliwell yesterday. The interest to keeping as much data as possible and feasible was growing all the time since the Protein Data Bank was founded. Initially, only atomic coordinates were deposed. Since 1999, PDB accepts structure factors for deposition, and they were mandatory, made mandatory in 2008. Since 2020, PDB accepts unmerged data sets. Not mandatory yet, but it doesn't accept the image data for clear reasons, and discussions are going on. I would like to make a point that the way this structure is solved represents a link between experimental data and final results, and therefore it is as important as the data itself. Revisiting a structure solution project may be useful for understanding how particular structure features were obtained, for education, templating, teamwork, software developments, and probably 1,000 other things which I'm not aware of. But at the moment, we have no framework for archiving and sharing structure solution project with the data. And this is something what I can imagine CCP4 Cloud can offer. This is how data logistics in MX field could look like in future. Experimental data may be made accessible via cloud and kept in link with structure solution projects conveniently for revisiting, sharing with colleagues and collaborators, and exposed to other researchers as necessary. With computing and storage costs coming down rapidly these days, it is not unimaginable at all that data and projects can be archived for practically indefinite time. This is, of course, slightly naive and primitive picture, and I'm far from thinking that depositing projects with the data should be made compulsory, or that it should be a single must-use cloud setup for structure solution, or even that today's CCP4 Cloud represents the ultimate and only choice. Certainly, we will always have a range of tools and approaches, and CCP4 Cloud only adds to that collection. And yet, I would like to come in the end of my talk, to the end of my talk with the statement that goals outlined in yesterday's lecture of John Halliwell are achievable, and we may have all needful technical means for that in our hands already. Finally, I should say that CCP4 Cloud brings us about an ease and a burden at the same time. It doesn't replace anything else in CCP4 project. It is built on top of everything else. But what it does, it simplifies the delivery of complex software, which is not so easy to install in local labs. It makes bug spotting and fixing and communicating with users incredibly efficient. And it is a tremendous help in CCP4 educational activities. Yet cloud development and maintenance is quite a chore, which pays off only at high usage rates. Therefore, please use it. And remember, cloud setup will be always greener than an equivalent number of local machines, and therefore save the planet a little bit by using it. CCP4 Cloud project enjoyed enthusiastic contributions from a number of people, and it makes me a real pleasure here to express my acknowledgements. It wouldn't be possible to create this modern framework without a significant collective effort, and I was fascinated with the support the project got from all the community. Funding from BBSRC and CCP4 is greatly appreciated. Last but not the least, we have a vacancy to work on a joint CCP4 EBI project funded by BBSRC. And this is in connection to some part of what David Armstrong presented today at in this session. Interested candidates are invited to apply, and do it quick, please. It's a January deadline. Please check job advertisement on CCP4 website and as well as on CCP4 bulletin board. Thank you very much. And now I'm open for questions.
Thank you for your talk. I can see questions yet, but someone typing in the Slack, maybe got some questions from there. I don't think it's a question.
Well, it is exactly 4:30. How this session should end.
Yes, we have some question. How long are your results maintained in the cloud?
Currently, we don't have any mechanism of deleting them automatically. All users have quotas for disk space. For as long as account exists, it will be there. I mean, we do not delete anything. A user can delete data, but not us.
And I think and how is computing resources such computer clusters, cloud computing handled at both different 5 installation, a common model, or all different? It's like
how is computing resources as such means cluster and cloud computing handled in those different 5 installations. All right, those 5 installations use different computing resources. They are actually different clouds. They do not communicate between each other. So each installations use domestic resources. This is it. I hope this is clear. Answer. A lab can use laboratory computers, an institute can use institute's cluster, and this is what happens. Right.
And the last question, how much power can be used in the cloud account?
Cloud accounts are created by default with 5 GB disk storage, 24-hour CPU every day. So next day it will be another 24-hour CPU, and 240 hours CPU every month. If that is not sufficient, you can simply pop us a message and we increase your load.
And I think the last question. Oh no, I think it's not about cloud in Q&A section.
This is not about cloud. This is something else.
So we shall move to wrap up session.